Solar radiation and Earth seasons. Well, the first thing we have to know in order to understand this is that every object in the universe emits electromagnetic radiation, what we could call light. Now, some light is visible to our eyes. We call this visible light, but there's plenty of forms of light that our eyes are blind to, like, for instance, ultraviolet light or X rays or infrared. Now, light is produced because anytime you take a charged particle, say a proton or electron, and you shake it, it makes disturbances in an electromagnetic force field, which propagate at the speed of light. Now, the faster you shake an atom, the shorter the wavelengths you get. And if the wavelengths are short enough, they tickle our eyes and we can see it. If you shake an atom fast enough, you'll see red light. Shake it faster, you'll see orange light. Shake it faster, you might see a bluish light. Shake it so fast, you may not even see it anymore. Now the waves are too small for eyes to see. We call this ultraviolet light. Shake it too slowly, and it makes waves that are so long that it doesn't activate the cells in our eyes, and we don't see it at all. We call this infrared light. So there's all different kinds of light that can be produced, and our eyes are only tuned to certain ones of them. Not just that the sun produces mostly light that we see, visible light, but also produces ultraviolet light and it also produces infrared. Now, you and I and the objects around us are cooler than what it takes to generate visible light. So we glow in infrared. So when you walk into the school in the morning and that camera tells what your temperature is, it's simply looking at the infrared light that your body is giving off and then interpreting that as whatever temperature the atoms in your body must be jiggling at in order to make that color of light. Pretty cool, huh? Now, the first law of thermodynamics is a very important one. And what it tells us is you can never create or destroy energy. You can only transform it from one form to another or move it from one object to another, but you can never get rid of it and you can never get more of it. So, what happens is when an object absorbs light and that light energy goes away, that energy has to manifest itself somehow. And it does it in what we call thermal energy. It makes the atoms vibrate. So, I have an atom here. It's not vibrating very fast. Light energy comes in. As it absorbs light, it jiggles faster. Now, what happens though is if it's jiggling faster, it's making light itself. So it's going to give off light. And once it gets rid of energy in the form of light, it's going to wiggle slower. So there's this interplay between atoms absorbing light and atoms producing light. So let's just keep it simple. If an object absorbs 1 joule of visible light, it's going to gain 1 joule of thermal energy. But if it gives off 1 joule of infrared light, then it's going to lose a joule of thermal energy. All the energy has to be accounted for at all times. Now, the sun is the surface of the sun is about 5,500 degrees. The core is over 10 million. But at the surface, it's the atoms are jiggling fast enough that they make the kind of light our eyes see. They make white light. So all the spectrums are visible, plus ultraviolet, plus infrared. Now, when this light gets absorbed by Earth, the atoms of the Earth warm up and they start to shake, but they only shake at a temperature of about 15 degrees. So that gives off infrared light. So there's this constant inflow of energy from the sun in the form of light and an outflow of energy in the form of infrared light from the Earth. I'll have a lot more to say about that later in the year when we talk about global warming. But let's just talk about this solar constant. There's a maximum amount of energy we absorb from the sun. And that is it when the sun's rays come down perpendicular and the energy is as concentrated as it can get. What we find is at the surface of the Earth, after passing through the atmosphere, there's about 1,361 joules of energy arriving at every square meter of Earth's surface at every second. Now, when we have energy flowing and it comes in a certain rate, the way we measure the rate at which energy is transferred between objects is in a unit called watts. 1 watt is equal to 1 joule of energy transferred per second. So since the sun is transferring 1,361 joules per second to every square meter, we could say that the solar constant, therefore, is 1,361 watts per square meter. Or if we prefer, 1.361 kilowatts per square meter. That's the maximum the sun can deliver to Earth's surface. But depending on where you are, it's going to deliver less than that. Here's why. All right, if you take a flashlight and you shine it straight down, its light, it makes a small spot. So all the energy coming out of the flashlight in the form of light is arriving at a fairly small area. But take that same flashlight and you tip it at an angle, and there's a fixed amount of energy. Let's just say it's 1 joule of energy coming out of here every second. So I have 1 watt of power arriving here, 1 joule per second. But now what's happening is I'm going to take that 1 joule and I'm going to spread it out over a larger area. So each unit of area is receiving less energy per second. This is why the Earth has seasons, and this is why it's cold at the poles and hot at the equator. It has everything to do with the angle of light. Now, I simplified my numbers here just to make it easier. Let's just pretend the solar constant is just 1,000. So if light rays are coming vertically and strike 1 square meter of surface, then I have 1 meter by 1 meter by 1 meter. I don't have 1 meter by 1 meter. I have 1 square meter. So I would say the energy density would be, and remember, I'm just rounding it to 1,000 watts per square meter. However, if I shine that light at an angle of 30 degrees, what I find is that energy is going to get spread out now. In fact, it's going to get spread out over twice as much area. And the way I could do that mathematically is I could just take the sine of this angle and multiply it by the solar constant. Since the light is coming at 30 degrees, the sine of 30 degrees is 0.5. So 0.5 times 1,000 gives me uh, um, 500. Uh, why is it not here? It gives me 500 watts. I thought, is it underneath? Where did it go? Oh, it's underneath this. You can't see it here. Darn it. Okay, there it is. All right, let me try moving this up here. I didn't know I could move that. That's so annoying. Okay, so it'd be 500 watts per square meter. And that's just because this is now spread out over 2 meters instead of over 1 meter. Now, oh geez, look at this. All right, it's driving me nuts. Okay, so why is it hot at the equator and cold at the poles? Well, it's quite simple. The rays of the sun are more concentrated at the equator, where the sun's rays come in basically perpendicular. And as we get closer to the poles, that same amount of energy is spread out over a larger area, delivering less energy per unit of Earth's surface area. So therefore, the energy is more spread out here, and so there's less energy arriving to make the atoms jiggle here than there is here. Now that explains why we have cold weather at the poles and warm weather at the equator. However, why do we have seasons? It has nothing to do with how close the Earth is to the sun. Believe it or not, the Earth is closest to the sun in mid-January because the Earth travels in an elliptical path around the sun. That has nothing to do with the temperature on Earth. What does have to do with the temperature on the Earth is the tip of the Earth's rotational axis. So, the Earth spins like a top. If the Earth's north pole pointed straight up at a perpendicular angle to what we call the ecliptic, which is just the orbital path of the Earth around the sun, if the Earth was spinning on its axis perpendicular to that path, then all it would matter is latitude. It'd always be warm at the equator. It'd always be cold at the poles, and there would be no seasons. However, the Earth's uh, rotational axis is tipped 23.5 degrees to the plane of orbit. And that is why we have seasons, because sometimes we're tipped well, we're tipped more towards the sun. In other words, the sun is higher in the sky, and sometimes we're tipped the other way, and the sun's rays are lower in the sky. And this is the main reason why we have seasons. Now, it's important to keep in mind that the seasons are the opposite between the northern hemisphere and the southern hemisphere. So when the sun's rays are when we're having summer in the southern hemisphere, we're having winter when we're having summer in the northern hemisphere, we're having winter in the southern hemisphere, and vice versa. Let's just talk about the northern hemisphere where we live. It makes it a little bit easier. So here's what we find. During the summer months, the North Pole is tipped 23.5 degrees towards the sun, which basically brings the sun's rays 23.5 degrees higher in the sky, allowing it to become more concentrated. Since the angle of the sun is higher, the rays are more concentrated in the northern hemisphere, and therefore we have hotter weather. Now, in the wintertime, our axis is tipped away from the sun, which brings the sun lower in the sky by 23.5 degrees, and that spreads its light out over a greater area, making it colder. So the reason it's warm in the summer is the sun is higher in the sky and its rays are more concentrated. And the reason it's cold in the winter is because the sun is lower in the skies and its rays are less concentrated. Now, there's 4 dates that are of note in the orbital calendar. And these are things that the ancient people knew about quite well. So things like Stonehenge and many temples around the world have been built with this in mind. And that is that on the 21st of December, That is the day at which the northern rotational axis, the north pole of the Earth, is tipped its maximum distance away, its maximum angle away from the sun, 23.5 degrees. Now, that's the very same day when the southern hemisphere is having their summer solstice because they're tipped 23.5 degrees towards the sun. But at any rate, we'll call it, instead of calling it the summer or winter solstice, we'll call it the December solstice. Now, 6 months later, we have the June solstice. So on June 21, that axis, the northern axis, is now tipped 23.5 degrees towards the sun, and the southern pole is tipped 23.5 degrees away from the sun. So that is the what we call midsummer's day in the northern hemisphere and midwinter's day in the southern hemisphere. Now we also have what are known as the equinox days. So the equinox occurs in March 22nd and September 22nd, and these are days at which the axis, the rotational axis of the Earth, is neither tipped towards nor away from the sun. So, in other words, if it's tipped 23.5 degrees away in December and 23.5 degrees towards in June, at the midpoint, it's not tipped either way. It's transitioning from being tipped away to being tipped towards, but it's neither on these 2 days. Now, get ready for this. Okay, so let's think about this. At noon on the equinox, where is the sun going to be in the sky? Well, here's where it's going to be. It's going to be take 90 degrees and subtract your latitude, and that's where it's going to be in the sky. So, for instance, let's just say you live at a latitude of 40 degrees north. That means at noon on the equator, the sun is going to be 50 degrees above the southern horizon. In other words, 90 minus your latitude gives the position of the sun in the sky 50. Think about this. What if you were at the equator? If you're at the equator, you're at 0 degrees. 90 minus your latitude means the sun is straight overhead on the equinox. If you're at the North Pole, it would be 90 minus 90, 0. The sun would just be right on the horizon. And if you're at 60 degrees, it'd just be 90 minus 60, it'd be 30 degrees in the sky, and so on. So it's just 90 minus your latitude equals the position of the sun in the sky at equinox. Well, then where will it be at solstices? Okay, so remember the tip of the sun is 23.5 degrees. So let's just say you were at 50 degrees latitude. At 50 degrees latitude, 90 minus 50 gives you 40. So at equinox, the sun would be 40 degrees above the southern horizon, assuming you're in the northern hemisphere. So at the winter solstice, it's going to be 23.5 degrees lower than that in the sky, 16.5 degrees at noon. And at summer solstice at noon, it's going to be 40 degrees plus 23.5 degrees. It'll be 63.5 degrees. So you can see between summer and winter, you have 23.5 plus 23.5. That's 47, is that right? 47 degrees difference in the height of where the sun is in the sky. So the main reason that it's hot in the summer is because the sun is basically 47 degrees higher in the sky in mid-June in the summer solstice than it is in the winter at the winter solstice. And here's just, oops, and you can just sort of see it's passing higher in the sky. But wait, there's more, because not only is the sun higher in the sky in the summertime, it's also in the sky for more time. The sun comes up earlier and sets later. Now, you might have noticed that it's been getting dark. Like you used to come to school, it was light in the morning. Now you're going to school, it's dark in the morning. That's because we've passed the equinox and we're moving towards the winter solstice. So we find is that let's just take Seattle, where I'm from. In the summertime, the sun is up for 16 hours during the summertime, but it's only up for 8 hours during the winter. So it's twice as many hours of sunlight in the summer than there is in the wintertime. So there's more sunlight coming for twice as long. So of course it's going to make it warmer. Now, the seasonal variation in daylight is pretty cool to look at this graph here. So this is the length of the day in hours, and we're just looking at the northern hemisphere. So here's the equator. At the equator, you know what? Every day is 12 hours every day of the year. It never changes. And if you've ever been near the equator, it's kind of weird. The sun goes down fast because it's not sliding down the horizon. It's coming straight down the sky every single day of the year. Now, what happens, though, is as we move away from the equator, now we're at 35 degrees north, we can see we have this much seasonal variation. So we see that we have more than 12 hours in the summer, and we have less than 12 hours in the winter. If we move further away to 50 degrees, Now we notice, my goodness, we have like, what is this, like 7 hours or so in the winter, and we have like 17 in the summer. If we move even farther away to say 65 degrees, we see, wow, so here it gets like we have like almost no daylight in the winter, and almost no night in the summertime. And then if we get to the actual pole, what we find is at the pole, it's really weird. At the pole, there's basically it's totally dark all winter long, and then you get to the solstice, I'm sorry, the equinox, and the sun comes up and the sun stays up all day, all night, and then you get to the next equinox and it drops below the horizon and it doesn't come up again until the next equinox. Pretty weird. Now, on the equinox, though, if you'll notice, every place on the planet has the exact same number of hours on the equinox, 12 hours. That's what's called equinox, means equal night. And that's the day when the axis is neither tipped towards nor away from the sun. Now, there are certain regions of the globe that have names that are indicative of the amount of light they get during the day, where the sun is going to be. So let's just start with this. If you start at the pole and you move 23.5 degrees away from the pole, from the North Pole, you get what's called the Arctic Circle. And if you move 23.5 degrees towards the equator from the South Pole, you come across what's called the Antarctic Circle. And basically, these are regions where at least at one day of the year, the sun never comes up. Okay, so at this point here, there's times of the year where there's complete darkness all day long and complete sunlight all day long. Now, if we come 23.5 degrees away from the equator, then what we find is if you come 23.5 degrees north of the equator, you're within what we call the Tropic of Cancer. And if you're within 23.5 degrees of the equator in the southern hemisphere, you're in what we call the Tropic of Capricorn. Now, what that means there is that in the tropics, there will be days during the year, at least one, if you're at the actual 23.5 degrees above or below the equator, there'll be at least one day where the sun is directly overhead. If you're anywhere within here, though, there'll be 2 days. One day when it's passing this way, and one day when it's passing that way. So within the tropics, there are days when the sun is completely perpendicular to the ground, maximum amount of solar radiation. So it's kind of weird. If you go to the tropics, you don't have to be at the equator. You just have to be within the tropics. There will be days in the year, or at least 2 days in the year usually, where the sun is directly overhead and you just don't leave a shadow. It's pretty weird. If you've never seen it, it's really neat. I had to do it I got to do it one time. It's really cool. Okay, now, you need to remember that these seasons are hemispherical in extent. So that means that when in the December solstice, it's winter in the northern hemisphere. However, that means it's summer in the southern hemisphere, and vice versa. When we're experiencing our summer, the southern hemisphere is experiencing its winter. And the last thing to say is that primary productivity, and biodiversity are basically dependent upon the amount of solar radiation coming in from the sun. And so within the tropics, those are the regions where we can get that solar constant amount, that 1,361 uh, watts per square meter. That's where we can get that. So that's why the tropics have so much productivity and therefore so much biodiversity, because they get so much energy there. And as we move away from the tropics, that amount of energy drops off. So productivity drops off and biodiversity drops off. Sorry, this was such a long one. It's kind of cool stuff. It's going to take you some practice to get good at it, but you'll get there.